In tick 1, we're going to write a COVID simulator. We want to find out how bubble size affects the R number. Here's how the simulator will work. We have a population. Each person is either infected or recovered or susceptible. We won't include deaths and we won't include reinfection in this model. Each day, we generate a set of locations, or a better word is loci, because they're not meant to represent physical places, they're places of contact. Each locus represents a place where a group of people mingle and, possibly, infect each other. It doesn't matter what the physical locations are, all that we're going to simulate here is the number of people associated with each locus. The goal is to understand what happens if there are government measures to limit the size of each locus. So for this simulator we'll just generate a random list of locus sizes. So we've randomly assigned people to loci. Next, count up the number of infected people in each locus, and we'll use this to model the infection. If there are any infected people in a locus, then each susceptible person might become infected. We'll say that each person gets infected randomly with a certain probability. Next, some people recover. Each infected person has a certain probability of recovering. We'll only apply this to people who are infected at the beginning of each day. We won't let people get infected and then immediately on the same day recover. Okay, so that's our simulator. The idea is that we'll simulate the epidemic for various different random distributions of locus size and see what effect it has on the R number. At this point, feel free to go away and implement the tick and stop watching, but I want to say a few words about why simplistic simulators are worth doing. Here's a notorious chart. It was presented by Sir Patrick Vallance, the government's chief scientific advisor, and it shows some scenarios about what might happen over the winter. He came under fire for this chart because the numbers on it seemed quite out of whack, and he got grilled in the House of Commons Committee on Science and Technology. His defence was, these are scenarios, not forecasts. He's really just splitting hairs. There are forecasts and projections and predictions, and they all mean the same thing. They are numerical guesses about what will actually happen. The only difference between a scenario and a forecast is that a scenario says, this is a forecast of what will happen if we take a certain course of action. In other words, a scenario is a counterfactual forecast. But basically, simulators for forecasting and simulators for scenario forecasting are just the same thing, and you ought to judge them by how accurate their predictions were in the past. That's the real test, the real way to evaluate scenarios and forecasts, and it was conspicuously lacking in all of Sir Patrick Vallance's presentation. If someone doesn't give you a clear answer about how accurate their forecasts proved to be in the past, you should be sceptical about their claims about the future. But there is a much more useful distinction to make between two different purposes of simulation. Here are two pictures. Which is more accurate? You could say the photo is more accurate because it's a faithful match for what there really is in the real world. Or you could say that the caricature is more accurate because it captures the essence, and that's what matters when it comes to trying to understand what's going on in public life and what the Prime Minister might do next. It's just the same with simulators. Sometimes you write a simulator because you want faithfulness, and you want to get out actual hard forecasts about what's likely to happen, and your simulation should be judged on how accurate its predictions are. But sometimes you want a simulator because you want to learn qualitatively what's going on. You'd use a forecasting style simulator, for example, to plan hospital capacity, but you'd use a caricature style simulator to learn general scientific laws like the R number is a key statistic that we should be tracking, or maybe the key metric is the number of superspreader events, not the average number of people in a place. I don't actually know about that last one, I'm making it up. But the point is, you should first of all do caricature simulations to learn what real-world parameters you need to measure, and then you measure them, and then you build a forecasting style simulator based on those parameters. You'll never be able to build a perfect replica of the real world, so you have to limit yourself to certain things you're trying to model accurately, and to figure out what you need to model accurately, you need to do a caricature simulator first. And the simulator we're looking at in this tick is most definitely a caricature simulator. It's not a forecast simulator. In fact, I'd go a bit further. Given what we know about how the pandemic spreads, which is very, very little indeed, It's dumb to try and write a simulator that tries to be as good a replica as it can possibly be. That's what Neil Ferguson's simulator is. It has an object for every person in the simulator, and it models care homes and airports and quarantining and all that stuff. And on the other hand, there are very crude simulators that just track the total number of infected and susceptible and so on, and they don't even bother to track individuals. Here's a nice plot from the New York Times, a survey of 7 different simulators. Here's Neil Ferguson's simulator, and here's a very crude one, by a data scientist called Yo-Yang Gu. Just because it's crude doesn't mean it's worse. In fact, the opposite. Because it's simple, it has less room for misfitting, and it's easier to calibrate it to the actual observed data, and then after calibration it will make better forecasts. So, we are building a simulator that's meant to be a caricature, not a forecast. And our simulator is just a little bit more detailed than Yo-Yang Gu's, but it's way simpler than Neil Ferguson's. Finally, a remark about coding. This tick is designed to test if you can use numpy. The point of numpy is that it's way faster than Python for loops, but it does take some creative thinking to figure out exactly which numpy operations to use. That's what this tick is all about. So every time you need to loop over the population or over the loci that people go to, you must use numpy operations. We'll simulate a population of size 50,000, and even at that size, Python for loops are too slow.